second period. Okay, starting now. Okay, hello everyone. This is for second period. So, based on the warm up from yesterday, I messed up terribly, unfortunately, but I figured it out by fifth and sixth period. So this is what happened. So we figured out that Dwight's and Michael's watermelon will have the same change in the momentum. Y'all remember that from yesterday? So it's because due to P equals mv, both watermelons have the same mass and velocity. Yes, same mass and velocity. And because they have the same mass and velocity, therefore they will have the same momentum. And both watermelons are in free fall, therefore both watermelons will have the same velocity, change in velocity as they are falling. The trampoline will, whenever we look at the trampoline and the car, they both will cause the object to have the same change in momentum. However, the trampoline applies a small force in a large time interval, which explains why the watermelon doesn't break, and the car will apply a large force in a small time interval, which explains why the watermelon does break. So large force equals more broken bones. Smaller force equals less broken bones, right? Okay. Yeah. So due to PFAT, the change of momentum is going to be the same in both cases. So when you multiply the force and time together, you will get the same momentum, which backs up why both objects have the same momentum. So let's move on to example 3 real quick. So my fifth period is for everybody listening to this video. My fifth period is just listening to me talk. So example number 3, Sydney Q is practicing her diving skills. Spencer comes along, suggests that she jumps off the side of a building. Why would you do that, Spencer? And then land on a cushioned target. So, because Sydney thinks it's a bad idea, Spencer wants to convince her. So, if we want to decide how fast he's falling, we know that Spencer falls off the side of the building at free fall. So that means we can use our kinematic equation or we can use our energy equations. So either way, both will give us the same equation. So right over here, we have this equation and this equation. This is my energy equation and this is my kinematics. Both will give me 30 meters per second. It doesn't matter what method you use, you'll get the same answer. So he takes the jump and lands on the target. It takes 1.5 seconds for his body to fully come to rest. So whenever we read that there, that's going to be the time interval that it takes for the object to stop and to stop being applied the force. Okay, so that means we have a change in momentum with this mass and velocity. We found this mass and velocity from the last question, and it's going to be 2400. We know if you want to find force, then we have to use JFAT. So JFAT is going to be J as in 2400 because J will equal P. So J will equal P. And then if we want to find force, we just algebraically solve for it, and it's 1600 newtons. Going on to letter C, if he demonstrated this in a pool, this explains to us why it hurts so badly to belly flop into a pool. So because you increase the surface area when you're jumping into a pool, then his body would feel the impulse applied to him. Like his whole body feels the force instead of just his hands. So if you're belly flopping, then your head, your muscles, your legs, your belly is going to feel the force. Whereas when you're diving, your hands would be the only one that feels the force, and it wouldn't hurt as much. So the change of time that it would take for Spencer to stop would be very small because he's literally flopping on the water, while whenever he dives, it would take quite a bit of time for him to stop. So remember, whenever you're diving, you're usually going and you're like underneath the pool, and whenever you're underneath a pool, you're still moving until you stop. So it'd be a very large time interval. And then whenever, and then, okay, so the time interval would be very small and the force would be very high. Whereas if you're diving, then the time interval would be very high and the force would be very low. So momentum would be the same in both the belly flop and the dive. The only thing that changes is the force and time proportions. Lastly, what does the negative sign of the force mean? It means that force is going to be in the opposite direction. So Spencer is going down here. He is applying a force to the water. The water is applying an equal and opposite force to Spencer, according to Newton's third law. So let's go on to the next part. So the next part, we have a 0.07 kilogram block, which is being slapped by a student with an impulsive force of 10 meters per milliseconds. Because the slap was performed by a student, he does not provide a robotic, consistent force. So as you can see here, we have a force that is increasing, stays constant, and then decreases over 10 milliseconds. And we know that if we want to find the impulse delivered to the block by the student, then we need to find the area under the curve. So the area under the curve is always going to be your impulse, okay? So we also know that J equals change in P. So J app is going to be J equals change in P. So that means we have to find the area of the trapezoid. So we find the area of the trapezoid. One side is going to be 10 milliseconds. Another side is going to be 4 milliseconds. So 10 milliseconds here, 4 milliseconds there. And then 20 is going to be the height of the trapezoid. Okay. So from here, you can just put it into your area equation and you will get 140. But if you want to convert it to, so as you can see here, we use milliseconds. We want to convert it to seconds. So we're going to move the decimal 3 places to the left, and you will get 0.14 kgms, which will always also be change of momentum, 0.14 kgms. So if we want to find a velocity, then we need to use our P math equation. So that's going to be 0.14 equals 0.07, that's given to us, equals times velocity. So velocity will be 2 meters per second. Okay, so that's what was supposed to be done yesterday in second period, although it wasn't done. So we're going to move on to what we were doing today for SAT day, where all the juniors were doing the SAT. And my fifth time around, video recording now. Okay, conservation of linear momentum of system of objects. So far, we've only talked about one object at a time. Now we're going to talk about multiple objects interacting with each other. No way, I know, it's crazy. So in a system, objects will interact will experience equal and opposite changes in momentum. So that's very similar to Newton's third law, which is equal and opposite reaction. Every action requires an equal and opposite reaction. So, when in terms of momentum, the conditions for this to happen need to be that it is an isolated system. So go ahead and write that down. And there is also, in an isolated system, are there external forces? No. If there were external forces, that would make it an open system. Whoa, crazy, I know. No external. So that brings us to the conservation of linear momentum. That's going to be a law that you may or may not can use on your FRQ. What? So this conservation of linear momentum, it's going to be very similar to your energy equations, where you know how energy, we have E equals E? Well, guess what this is going to be? Momentum equals momentum. Yeah, P equals P. So the total momentum before collision is going to be equal to the total, I did not write that properly, total momentum after a collision. Okay? So P equals P. The momentum before equals the momentum after. In an isolated system, momentum will remain constant. So that means momentum is, what is that C word? What's another C word? Con, almost. Almost. Con. What is something that we use in energy? Con. Con. Conserved. Conserved. It's very similar to continuous and constant, but conserved, that's the key word. Oh, it's total momentum before equals total momentum after. This is total. My bad. So according to Newton's third law, what is an action-reaction pair? Right? We already stated that Newton's third law is going to be every action requires an equal and opposite reaction. So that means an action-reaction pair has to do with forces. So if I have a ball that is being thrown in this direction by this little dude over here, he's like throwing this ball. Right? So he's throwing that ball. So if he's throwing that ball in that direction, that means there is going to be an equal and opposite force opposing him. So that means this is going to be the force of the person, and then this red part is going to be the force of the ball on the person. So that's an equal and opposite reaction. So what I would like for you to do now is to take about 3 minutes to do this thing pair share. So you're going to think about it. So you're trapped floating in the space near your shuttle, dubbed STS Storm Spiked or ISS Ragnarok, whichever name you like better. When you realize that your cord has snapped and disconnected from the shuttle, what do? And just a hint, me and Mr. Chaudhry took like 5 minutes trying to think of a shuttle name. So we like went on the internet, and then the internet gave us like a bunch of names, and we settled on STS Storm Spike and ISS Ragnarok. It was pretty cool. So take about 3 minutes to do that. Okay, so things that you would do, you could poke a hole in your suit, like in Martian. You probably would die, but I don't know. I guess you have to strategically poke a hole so that it doesn't impede your airway. I don't know how. I never watched The Martian. Yeah, it's in The Martian. Hold on, pause. And 1. Okay. So things that you would do, you would poke a hole if you are smart. I don't know. You would get a fire extinguisher if you were Wally. Y'all know that scene in Wally? Yeah, where Wally has a fire extinguisher and he just moves because he's using it. Or you can throw something. Okay, so you can throw something. Things that you wouldn't do, you should not swim. Okay, so that leads us to our question. An astronaut is floating in space near her shuttle when she realizes her cord has snapped and disconnected from the shuttle. Her total body mass, which is her body, suit, and equipment, is 91 kilograms. So she reaches into her pocket and finds a 1 kilogram metal tool, throws it out into space with a velocity of 9 meters per second directly away from the ship. If the ship is 10 meters away, how long would it take for her to reach it? So let's draw this. So we have a ship. We have astronaut looking guy. Looks like marshmallow. Could be a marshmallow. Woo. 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 Oh, shit. So he has his little tool thingy, his little wrench.
Did you use the wrong pole this morning?
What do you mean the wrong pole?
You wrote WHOLE in your suit instead of HOLE. What?
Hole? Oh, really? Yes. Like hole? Whoopsies. I don't know what I was thinking. Okay, so he throws this at a velocity of 9 meters per second. So that means he travels at some sort of velocity, we don't know that, towards the ship. So what I want y'all to decide, so let's pretend this is 0, and then this is a number line. So where's my positive direction? Where do you want my positive direction to be?
Right.
The right or the left? Right? Okay. So you want it to be right? Okay. So you can choose it. It doesn't matter. And then your wrench can be in the negative direction. So that means we're going to use this equation. So we have our total momentum before, okay? So this is going to be momentum before is going to be equal to momentum after, okay? So momentum before is going to be the total momentum of the wrench and the astronaut. And then the momentum after is going to be equal to 0 because we don't want there to be any change. Um, okay, that was weird. Okay, because these momentum is conserved. So then after it's going to be 0. Okay, so it's going to be 0 because momentum is conserved. And then this is also what we call an explosion. Explosion, right? So the mass of the astronaut, which is, so then if we want to solve for the velocity of the astronaut, we have to get the velocity by itself. So then the v of the astronaut is going to be equal to negative mass of the tool times velocity of the tool over mass of the astronaut. So then that's going to be equal to negative, what is the mass of the tool?
1 kilogram.
1 kilogram. Tool? Is it 9 or negative 9? Negative 9. Yeah, so don't forget that negative because it's in the negative direction. And then the mass of the astronaut? Mass of the astronaut. 91 kilograms, yeah. So then essentially, these negatives cancel out into a positive, and then our answer will be 9 over 91. Someone do that in their calculator real quick? Or let me just look at the answer from point one. So my answer is going to be 0.1 meters per second. So it's going to be positive 0.1 meters per second. So we can say that the astronaut travels at 0.1 meters per second. We also need to find out, what is the question asking us?
How long will it take 10 meters away?
Yes, how long will it take for her to reach the spaceship, right? So the distance between her and the spaceship is going to be 10 meters, right? So it's like, wee, that's 10 meters. So we know that velocity equals distance over time. So that means distance is 10 meters. Time is going to be 0.1 meters per second. So if we multiply that out, we get 100. Oh, wait, what was I doing? Oh, okay. So then whenever we change it up, we can just switch these places. So we have velocity and time switching places. So then that means time is going to be equal to distance over velocity. So we're solving for time. So whenever we have that, we have 10 meters over 0.1 meters per second. And then our time will be 100 seconds. Okay? So just to recap, we used our conservation of momentum equations where the momentum before is going to be equal to the momentum after. So from here, we have our 0 here because momentum is conserved and it's an explosion. And then we solve for velocity of the astronaut. We got 0.1. We plugged that into v equals dt, solve for time, and then got 100. Okay, let's move on to the next part. Last page. Woohoo! Last page is collision, so it's also there. So everybody, give me examples of collisions.
A car collision slash rear ending.
Spencer, stop looking at the answers. What's up, Michaela? Cars colliding. Okay, cars colliding.
Touching someone.
Oh my gosh, be more creative. I don't want to hear second period's answers.
I am second period.
Okay. Throwing something at a wall.
Builder arrow trampoline. We can try that right now. Jumping outside the window.
Jumping.
From the window.
From window.
Ball bouncing. So I have another collision. Okay, let's try.
Wow. You're so right. Ball bouncing.
Who would have thought?
Examples of explosion. Spencer, stop looking at it.
Ooh, fireworks.
Fireworks. Oh my gosh.
Something 1945 tanks.
Oh my gosh. Russia versus Ukraine. Woohoo.
That's
Okay, I'm not ready. Okay, I'm not including that actually. This is a video. Okay. Okay. What else?
Nitroglycerin.
Oh my gosh. Okay, fireworks is good enough. Okay. Oh, throwing something at wall. Yeah. Okay, so let's go on to types of collisions. So what I want to show you right now is going to be, there are 4 types of collisions. One thing about this is that an elastic collision and a perfectly elastic collision are going to be the same. So the thing about an elastic collision, that's going to be when something bounces off of each other. So we have Mateo Don, focus. Mateo Don, focus. So we have, say, billiard balls. So we have this billiard ball. It's going to be approaching this ball that is at rest, right? So what happens to this ball whenever it hits the ball? Does it keep going or does it stop? It will stop, right? So after collision, it will stop. It stops. Okay? So we have that, and then we also have this situation. So let's say these 2 balls are going towards each other, and then as a result, these balls will collide, and then they will bounce off of each other and move away from each other, right? So it's so they're going to be bouncing. So they're going to be bouncing against each other. There's going to be no sticking involved. Okay? So then perfectly elastic is going to be the same as elastic. So I'm just going to write same. Going on to elastic. In an elastic collision, momentum is actually conserved. So we never lose momentum or anything. Okay? So that's going to actually be the same for all collisions. So momentum is conserved for all collisions. Okay? So say you bump into someone, all that energy gets transferred into something else, right? And all your momentum will actually get transferred into momentum as well. However, the difference between momentum and kinetic energy is that kinetic energy may or may not always be conserved, right? So an elastic collision, because if we look at the situation where this billiard ball hit this other ball will start as a result. So this ball stops, and then this other ball starts moving. Okay? So all that kinetic energy from this ball, this initial ball, transferred to that other ball. So that means this other ball will start moving at a certain velocity because its kinetic energy was conserved. Okay? Okay, so wait, let me just move my camera down. There it is. Okay, so in an inelastic collision, kinetic energy is actually not conserved. Oh my gosh. And even worse, a perfectly inelastic collision, kinetic energy also is not conserved. Okay? So, examples of an inelastic collision. That's going to be whenever whenever you rear end someone. Okay? So, whenever you rear end someone, whee, I hope you never rear end someone. So this is going to be rear ending someone. Yeah, but he never took my insurance, which is good.
I'm gonna ask him.
I know. He was like, it's fine. We just drove off, and I was like, thank God. So what? Okay, so if a crash ever happens, what are cars designed to do?
Crumble.
They're designed to crumple. Yeah, and this yeah, and this crumpling motion is designed to protect you from getting hurt, right? So if it wasn't crumpled, then all that movement, you're going to feel all that movement, you know? However, that kinetic energy will get lost because it's crumpled. So because it crumpled, all that speed and all that kinetic energy will not affect you as well. So, so whenever you rear end someone, usually after the rear ending, do you continue moving? Yes, you're gonna move a little bit. Maybe not as fast as before, but you're still gonna keep moving. Yeah, is the other person gonna move?
Yeah.
Yeah, they're gonna move too, right? Yeah.
If they're in neutral, if they're reversed though, they're gonna stop.
Yeah, but they still like get that jolt, That's still movement. So, yeah, so in this situation, kinetic energy will be gained or lost. Okay? And in a perfectly inelastic collision, let's talk about that. So in this case, usually whenever we have perfectly inelastic collisions, that usually happens when things stick together. So in car crashes, have you ever seen a car crash where the cars stick together? Hopefully you never do. No? Okay. Well, sometimes it happens. And these cars will stick together and they crumple. And when they crumple and become one car, essentially, do they keep moving? Yes, they still move a little bit, right? So they crumple and they still move, but the key word is that they stick together, okay? So they stick together. That's what defines a perfectly inelastic collision. Inelastic collisions, it doesn't necessarily mean that the objects stick together. It only means that kinetic energy is lost or gained. However, in a perfectly inelastic collision, the max amount of kinetic energy possible will be lost. Okay, not necessarily gained, but in this situation, the most amount of kinetic energy that it could possibly lose will be lost. Okay? Okay, so that's all I have for y'all today.